Okay, good afternoon. Should we start? So, we are going to continue today with the ISA, the instruction set architecture. We will continue talking about the ISA in LC3 and in MIPS. And when we finish with that, probably around the time of the break, we will continue with assembly programming. We are going to talk also about assembly programming in LC3 and in MIPS, and we will see what are the most common programming constructs that you're going to need, for example, in the labs. So this is the agenda for today, and for the next few lectures, we will finish the ISA for LC3 and for MIPS. And then, as I said before, we're going to talk about assembly and programming. And for the next lectures, as I mentioned yesterday, we will start, or Professor Mutlu will start with microarchitecture, single-cycle microarchitecture, multi-cycle microarchitecture, and microprogramming. Just to remind you what are the readings for this week and for next week. If you compare these to the slide in slide 9, you will see that we have included this chapter 6 because that's the chapter in Pata and Patel where programming and debugging is explained. So keep that in mind and read it as well. So what we will learn today. We continue with the ISA in LC3 and MIPS, operate instructions. That's the first thing we are going to talk about, or we continue from the point where we stopped yesterday, data movement instructions, control instructions, and then also for each of these type of instructions, the instruction format and the addressing mode. When we finish with that, as I said, we will go to the assembly programming. We will talk about the most useful programming constructs, how to debug assembly program, and then we will go to the MIPS assembly. We will see how to build conditional statements and loops in MIPS assembly, and we will also talk about some other issues like how to work with arrays in MIPS assembly, or how to do function calls. We will also mention the way this is done in LC3. And finally, the stack. I will explain what the stack is. Before going through all these contents, let's quickly recall what we were talking yesterday about. We presented the von Neumann model. I'm sure you remember this slide. You can see here input and output components, the memory where we store programs and data, the processing unit where the instructions are executed, the operate instructions are executed on the ALU, and finally the control unit, which is the where we have the final state machine that controls the performance of all the machine. And for sure you also remember this slide which is the LC3 computer, again with the control unit, processing unit, memory, inputs and outputs. Recall that yesterday we explained how the instructions are executed on this data path, and we said that there were 6 possible phases. Not in all cases these 6 phases are executed, but in summary, these are the 6 phases that the instructions have to go through to get executed. The first 2 are common for all instructions, fetch and decode. Remember that in fetch, we read the instruction from memory and put it in the instruction register. In the decode stage, in the decode phase, the finite state machine checks what's the opcode in order to identify the instruction and generate the necessary control signals. In some instructions, like those where we have a memory access, we need to evaluate address, like in loads and stores. and fetch operands. We can fetch operands from memory in some cases. We fetch operands from registers in other cases, like in the case of the operate instructions. And then we execute, typically in the ALU for the operate instructions, and we store the result in register or in memory. Recall that this is called the instruction cycle because every time we finish with the store results phase, we start again for the next instruction with the fetch phase. And also recall what's the instruction set architecture. It's the interface between software and hardware. And as you already know, this ISA specifies the memory organization, the register set, and the instruction set. And that's what we are talking about. We started yesterday talking about the instructions, and we continue from this point with the operating instructions. The first one of them is not in LC3. You remember that we already presented this one. Well, in LC3 also remember that we have unary or binary instructions depending on the number of operands that we have. In MIPS, all of them are binary instructions. And for not, this is the syntax in LC3 assembly. This is the matching code, and this is the relevant data path. We have a source register. We go. We input this source register to the ALU. The ALU will receive some control signals from the finite state machine that will tell it you have to execute one not operation. It will invert or flip all the bits and store the result in the destination register. We also talked yesterday about how to implement not in MIPS where we don't have not. And as one of you said, this is possible using NOR or NAND. Okay, let's continue with operate instructions. And now we are going to talk about first those operate instructions that use literals or immediate. You're already familiar with literals and immediate. Now we are going to see how these are used in operating instructions in LC3 and in MIPS. Afterwards, we will talk also about something that is important and is necessary. It's subtraction. How are we going to execute subtraction in MIPS and in LC3? So we will see this in a couple of slides. So let's first take a look at the operating instructions with a literal. For example, for AND and add, this is the format. This is the instruction encoding. Observe that the five least significant bits are this IM5, which is the literal or the immediate. And I guess that I think that you should remember the rest of fields. The first one is the operation, that it identifies the operation that we will execute on the ALU. For add, this opcode was 0001. It's exactly the same opcode as in the other register mode add that we presented yesterday. And this is the semantics for this instruction. We take this the contents of this source register and we add the immediate. As you see, we need to sign extend. You will see in the next slide how we do this sign extension. For AND, everything is very similar. The only thing that changes is the opcode and, of course, the semantics, because instead of doing an addition, what we are going to do is a bitwise AND. This is source register 1, destination register, and the immediate that will be sign extend to 16 bits. Why is it sign extend? Why do we need to sign extend? Because we need to convert from 5 bits, that is what the operand that we really have in the instruction, to 16 bit, that is the number of lines that we need to input into the ALU. This is something you can see here in this slide. Here in our instruction register, we can see that the 5 least significant bits contain this immediate operand, this literal, And here, using this unit that you see, we extend. Essentially, this means taking the most significant bit and replicating it to the rest of lines, right? So from 5, we go to 16 lines. What the ALU is going to do is taking this input, the immediate operand, and the other operand will be the source register, and in this case, we perform an addition. Then finally, we store the result in the destination register. There is something interesting here to observe, is that we have this bit, this single one that you can see here, that is controlling this multiplexer that chooses between the literal, the immediate operand in the instruction, or potentially 1 second source register. You will see this later again, but this is the main difference that we can find between the addition that uses 2 register operands and the addition that uses 1 register operand and 1 literal. This is what is called an steering bit in LC3, because this bit determines how the rest of bits of the instruction, those bits that are after the steering bit, are interpreted by the hardware. When you look at the other add, the add that uses 2 source registers as operands, you will see that the value of this is 0, corresponding to this input of the multiplexer. Okay, so how do they look, these instructions with, these operating instructions with literal in MIPS? Again, they have 2 register operands and they have 1 immediate. One of the register operands will be the destination, RT, and the other is the source, RS. And then we have the second input operand, which is the immediate. This instruction format that is called the I-type in MIPS, it's used in some operating instructions, like the ones we are going to see now, and in data movement instructions. You might remember this from yesterday, where we talk about the LW yeah, the load word instruction in MIPS to access, to read from memory. So here have our opcode or operation, source register, destination register in some of the instructions, and source registers in other instructions. This is important to keep in mind, and in particular in store word that is used to write into memory, because in this store word we need 2 registers. One of the registers to calculate the effective address, to evaluate the address, and the other one is where we have the value that we want to write or store in memory. And this is the immediate. And now let's take a look at how this looks in MIPS assembly. Observe that here the mnemonic is different. It's not add, as it was the add instruction with 2 register operands. Here it is add I. The I obviously means immediate. These are the field values, and these are the semantics. Again, we have to, same as in LC3, we have to sign extend. In this case, we sign extend from 16 bits, which is the size of this immediate, to 32, because remember that 32 bits is the size, is the word length, the size of the quantities in MIPS. And this is the matching code, and we can also use the hexadecimal to represent the matching code. So those are the operand instructions using immediates or literals as operands in LC3 and in MIPS. Now let's take a look at another very important operating instruction, is subtract. How are we going to implement subtract in MIPS and in LC3? Well, in MIPS, it's really easy. For example, if we want to compile some high-level code like this, A = B plus C minus D, into MIPS assembly, we can write something like this. Here, let's say that S0 is B, S1 is C, and
S2 is D. So observe that we have two operations here. Because we have two operations, we have two MIPS assembly instructions. The first one is for the addition, the second one is for the subtraction. And finally, the result will be in S3 that corresponds to A. How can we implement this in LC3? In LC3, recall that we don't have subtraction. We only have three operating instructions in LC3, and, add, and not. We don't have sub. So how should we do if we want to subtract two numbers in LC3? Well, we need to do something like this. Before, I mean, this is exactly the same as this one here. Is an addition of R0 and R1. Assume that in R0 we have B and in R1 we have C. And then right after that we need to do these two instructions, not and add, that are used to calculate the 2's complement of register R4. In R4 we have D. So what we are doing here is taking R4, inverting all the bits, and adding 1. That's the way we calculate the negative of positive number, right? So what we're doing here is calculating this 2's complement, and then the result, this already negative number, R5, is added to the partial result of the first addition instruction. Finally, in R6, we will have the result for variable A. So this is another example of trade-off. If you compare two codes, you see that the functionality is exactly the same. The difference is that in LC3, because it's, let's say, a more simple machine, you need more instructions, but the good thing is that the control logic is simpler, the hardware is simpler, and can potentially run faster. So these are the trade-offs that we were talking about yesterday, and we will continue talking about them today. And one more thing, how should we implement subtract immediate in case we want to compile to assembly code or convert to assembly code some high-level code like this, A equal B minus 3. Here you see that we have a constant, so this is an immediate, right? Well, potentially we could have something like that, right? Sub I. This would be the destination register, this is the source register, and this is the immediate, 3. So this could mean subtracting 3 from S0. But is this really necessary? What do you think?
Can't we just calculate the 2's complement of 3 while writing the code?
Yeah, that's more or less the way we are going to do it. Actually, we don't even need to calculate we need to calculate the 2's complement if the value that we have is positive. But what we can do is directly writing something like this, minus 3. So, very good. And actually, in LC3, it's exactly the same. So here, we can implement in a very similar way the immediate subtraction in MIPS assembly and in LC3 assembly. Okay, so now we are done with the operating instructions for now, and now we are going to go through the data movement instructions and the addressing modes, because the addressing modes are here more important than in other types of instructions. So how many data movement instructions do we have? In LC3, we have 7 data movement instructions. Observe that these first 3 and these last 3 have like kind of similar name. The difference is that these are L from load and these are S from store. So they are equivalent, but the ones on the left are loads and the ones on the right are stores. And then we have this 7th one, which is LEA. You will see next how we implement it. This is called load effective address. Same as before, we have opcode in each of the instructions. We have destination or source register. Observe that here one of the operands is coming from memory and the other one is in a register. So we might want to move data from register to memory or from memory to register. So that's why in these instructions we will have destination register or source register. And then we have some address generation bits. The way we interpret these address generation bits is called the addressing mode. We already talked about that yesterday. And there are several types of addressing mode. We have the PC relative mode, we have the indirect mode, Base+Offset, you are already familiar with this one, and immediate mode, that is more or less, it's something similar to what we have just discussed for the operating instructions. In MIPS, we have more or less the same addressing modes, but not exactly the same. For example, in MIPS, exactly. In MIPS, we have Base+Offset. I already discussed this yesterday for dot word, but we will see it again. And we have immediate mode. We have something similar in MIPS for the PC relative mode. We have something similar than the PC relative mode, but it's not for data movement instructions. It's for branch instructions, as we will see in the next part of the lecture. And in MIPS, we don't have this indirect mode. So let's start with load and store, LD and ST. This is the encoding. Observe that here we have the opcode, the different opcode for load and store. We have the destination register in LD or the source register in ST. And these are the semantics for LD. We access memory using the address that is generated by using the incremented PC plus sign extend the PC offset 9. So for the same reasons as before, that we remember that we had to sign extend from 5 bits to 16, because 16 is like the number of lines that we input in the ALU. Here are going to do exactly the same. This PC offset that has 9 bits is extended to 16 bits. And this is the program counter. So this is PC relative, because as base register, we are using the program counter. The reason why this PC is the incremented PC is because as soon as we fetch one instruction, we increment. Recall that we increment the PC. So when we use the PC to evaluate the address and the execution of this instruction, the PC that we are using is already the incremented PC, and that's the same in the rest of instructions that we will use the program counter. And the semantics for ST are more or less the same, but here we have a source register whose contents we store in one memory position. Okay, so how is this LD? Here is the LC3 assembly for LD. How is this LD executed on the data path? So observe that we have our instruction register and the incremented PC here, or the PC that has already been incremented. And what we do is adding the PC plus the immediate operand after sign extension. The result is going to be loaded into the MAR. Why is that? Because we need to load the address in the MAR to access the data that is stored in that address. One interesting thing here is that this add component or add element that you see here is not the ALU. It's a separate adder that the data path has. You will see later where this adder is located. So let's take a quick look at the steps. We first calculate the address in the adder, then we read from memory the address that has been stored in the MIR. The memory moves the data element that is going to be read to the MDR, and finally in the third step, the destination register is loaded with the value that was just read from memory. So is this useful? Yeah, obviously this is going to be useful, but it has one limitation, and the limitation is that because this PC offset 9 can also contain only 9 bits, we cannot address memory locations that are very far away from where the PC is in one given moment. Essentially because what we are doing here is adding to the PC one number that is between 256 and minus 256. So that's why, let's say that this is the limitation. We cannot reach very far away from where we are executing the program if we are using this instruction. But this is not really a problem because we have other ways of addressing memory. For example, in the indirect addressing mode, and here we have LDI and STI are the two instructions that we have in LC3. Again, we have PC offset 9, but now the way we are calculating the effective address and the way we access memory is different. Observe that this is an indirection. This is something like having an array of pointers in C that can be useful for defining some special data structure, maybe the 2-dimensional, 3-dimensional data structures, for example. And observe that what we are doing here is that we calculate we calculate one address in the same way that we did in the previous instruction, but then with this address, we access memory, and we read something from memory that is actually an address to access memory again. That's what this is an indirection. We calculate an address to access another address to access memory again. These are the semantics for STI, and now let's see how we execute, in this case, LDI, on the data path. We have our instruction register. This is the literal PC offset 9, the incremented PC, same as before. We calculate one address that is stored into the MIR. We are going to access this address in memory. We read something from memory and observe that this, whatever that we read from memory that will be copied to the MDR is, in this step 2, moved from the MDR to the MIR, because that's the address that we are going to use now to access the final element that we want to store in the destination register. So in the 4th step, we read from memory again. The final value will be stored in the MDR, and from there, loaded into the destination register. What's the good thing here? Now we don't have this limitation of how far can we go away from the program counter. Now, because we are reading something, the very first read that we do in memory, from memory, is something that is an address. This can be whatever address in memory. So now we can access any operand anywhere in the memory. Okay, so now let's see Base+Offset very quickly, because you're already familiar with this. You're already familiar with LDR and with, not with STR, but it's essentially the same. The opcode changes in 1 bit, as you can see. DR is the destination of the register in LDR, SR, the source register in STR, and we also have the base register. We have the offset 6. In this case, the immediate is 6 bits. We sign extend, and we calculate the effective address in this way. How is this executed in the data path? In somehow similar way as before, but now instead, so if you compare this, for example, with the PC relative addressing mode, it's more or less the same, but instead of using the PC as the base register, here we use one general purpose register as the, in this case, for example, R2 as the base register. So again, we use this other, we add the base register and the sign extended operand in the instruction. We calculate the address, we read from memory, and finally we store the value that we just read from memory into the destination register. Again, the good thing in this LDR is that we can access also anywhere in memory. How is this in MIPS? So very similar way. For LW and SW, load word and store word. This is the MIPS assembly for store word. You can compare it to load word. You will see that it's exactly the same. The only thing that changes is the S instead of the L. And also the fact that here, S3 is the source register, because that one contains the value that we want to write into memory. So these are the semantics, and these are the field values. The opcode obviously also changes with respect to load word. And here, same as we do in the operating instructions with immediate, we also need to sign extend, in this case, from 16 bits to 32 bits. Okay, let's take a very quick look at an example in MIPS and in LC3. This will be the code in high-level language. Here you can see that we are reading, we are accessing memory to read this element 0 in array A. We copy it into variable A, then we add something to this A, like B, and then we subtract 5. We store that partial result, the temporary result in C, and finally we store this result into the final destination that is the first element, or element 0 in array B. So this could be our registers for MIPS. We can map the address of array A into S0, B into S2, and the address of array B into S1. So for the MIPS assembly code will be something like that. We first need to read from memory with this load word instruction. We are calculating with this immediate operand 0 and this base register S2 that contains the address of the array. We calculate the effective address, we read from memory, and we store the result in T0. Then we add, in this case, the contents of B, then subtract 5, and then store the result in somewhere in S1 plus 0. Recall that S1 is the address of the array B. So what are we storing? We are storing the contents of the temporary register 2. We can compare this to LC3, and we can see that it's exactly the same. So we sometimes talk about trade-offs. In some cases, some piece of code is longer or shorter in LC3. Here, they are exactly the same, and that's essentially because this instruction, load word and LDR and store word and STR have the same functionality, and they operate in a very, very similar way. Okay, now we are very close to finish with the data movement instruction. The last one is load effective address. Observe that here in load effective address, what we do is storing in some destination register one address that we calculate from the PC and the offset and the literal that we have in the instruction. One question here, because we have already done something like this before. We have already used the PC as the base register and have added some offset to this PC, right? But that was in LD, if I recall correctly, right? What's the difference between LEA and LD?
Well, here we are storing the address in the register and not the memory that's at the location.
Exactly, very good. So that's the difference. We compute the effective address in the same way, but in LD, we go to memory, we read some operand, and we store this operand in the destination register. And here, what we are storing in the destination register is an effective address. Okay, how is this implemented or executed on the data path? It's something like this. We have the instruction register, this is the offset, the incremented PC, we assign extend the offset, we add them, and we directly store the result of this addition into the destination register. There is something similar also in MIPS, but it's not exactly the same. It is called load upper intermediate, and here we are not going to use PC relative addressing. Here we store directly some immediate, some literal into the 16th most significant bits of one register, the destination register. This, as we will see at the end of the lecture, is useful when we want to work with arrays, because this allows us to store one 32-bit element, for example, one 32-bit address, into some array for different purposes. The purposes, as you will see when we talk about this again, will be accessing one array that starts in one particular address. So the way we are going to do this is like this. Observe that this is the 32-bit value that we want to store in our register. In this case, is register 0. So what we do is that the 16 most significant bits are here, the immediate operand of this LIU instruction. This LIU instruction essentially copies these 16 bits into the 16 most significant bits of S0. And then we just need to OR S0 with the remaining 16 bits, with the 16 least significant bits of the value that we want to store. We will see later again how to use this. Okay, so now before finishing with the data movement instructions, let's take a very quick look at one addressing example in LC3. So the question here, this is some matching code, okay? We have here like 7 instructions. And the question here is, what's the final value of R3? Well, what's L3, R3? So R3 is the, you see, the destination register here in this last instruction. But because this is quite difficult to understand the way it's right now presented, let's take a look at each of the instructions. The very first thing that I've done here is giving you what's the translation to some human readable representation, right, of these opcodes. And you see that these instructions are IL, EA, add, ST, and etc. Now, what are the immediate operands, the literal that these instructions have? That is simply to make easier to understand what each of these instructions does. So this is -5, this is 0, this is 5, 14, and this is -9. And then let's take a look at what each of the instructions does. So the first one is ELEA, so it's a load effective address. Recall that in load effective address, what we do is storing the result of adding the PC plus some immediate operand into a destination register. And here, what is the destination register? It's R1. So what we do here is that we are storing in R1 the result of PC -3, that is this literal that we have here. Observe that the result, because this is the incremented PC, and the incremented PC is the address of the next instruction, the result is this address -3, so it's 30F4, so something around here, one address around here. So the next instruction is R1 plus 14, is an addition. This is the destination, R2, this is the source, R1, and this is the immediate operand, 14. So what we are doing is that we are adding the address that we just computed before, plus 14. So this gives us 3102, that will be something, one memory address around here. So we continue with this ST. In ST, we store something in memory, right? So we first need to calculate the effective address. ST is PC relative, so we use the PC -5, that is the immediate operand. We compute this instruction, this effective address. Observe that this effective address is the same address that we stored before in R1. And there, we are going to store what we have in the source register, that is 010. So its source register is R2, because R2 contains 3102, 3102. That's what we are storing somewhere in memory around here, in address 30F4. This is easy, right? So let's continue with the AND. With the AND, what we are doing is simply initializing R0. This is like an immediate AND, so we are ANDing R2 with 0. The result is 0. Now we initialize R2 by adding 5, so the result is R2 equal 5. And here, this is a store register. Observe, in a store register, we have one base register that is register 1. We have one source register that is register 2, and we have some immediate 14. So what we do is writing in memory, in particular in this memory address that is R1 plus 14, and R1 contain 30F4 plus 14, this is 3102. Remember that this was some address around here. So what we are doing here is that we are storing somewhere here the number 5, which is what register 2 contains. And the last thing, and this is where we can see what's the final result that is stored in R3, we have an LDI, so this is indirect memory addressing mode. First of all, we calculate one address, is PC minus 9. PC9 minus 9 is exactly 30F4, somewhere here. We go to, we go to 30F4, we read from 30F4, and there, recall that we stored in this instruction here, we stored one address that was 3102. So now we go to address 3102, we read the contents of this address, and it turns out that the contents of this address are 5. So we will put this 5 into the destination register that is R3. Is that clear? Okay. So yeah, you can take a look at this, and if you have any questions, you can ask me later. Now let's quickly go through the control flow instructions. So recall that these control flow instructions are useful when we want to change the sequence of execution. By default, what we do in a program is executing one instruction after the other. And changing this sequence of execution is useful in many cases. For example, when we want to call functions, or when we want to implement conditional, when we want to implement, for example, if-else statements, or we want to implement things like while loops or for loops. We distinguish between conditional branches and jumps, which are like unconditional branches. In LC3, as we will see next, in order to use these conditional branches, we need to use the so-called condition codes. We have 3 condition codes, as we see in the next slide. And yeah, for jumps can be used to implement loops or function calls. The jumps that we have in LC3, you already know J and P. We talked about that yesterday, and about J. So let's talk about the condition codes. What's the condition code? These are like, we have 3, and these are like 3 single bit registers, and they are updated every time one register is written. Recall that we have 8 general purpose registers. We write sometimes in these general purpose registers. For example, when we use the ALU, the result is stored in one of them, or when we use one load instruction, we read something from memory and we store in a destination register. Every time we write a destination register, every time we write one general purpose register, these 3 condition codes, these 3 single bit registers are updated. And the 3 registers are, condition codes are N, Z, and P. So depending on the value that we write, these 3 guys will have will be 0 or 1, will result in 0 or 1. For example, if the value that we write is negative, N is set, and P and Z and P are clear. So we will have NZP, so the result for the condition codes, if the written value is negative, will be 1, 0, 0. If it's 0, Z is set and the other two are clear. And if it's positive, P is set and the other two are clear. So using this, we are going to, so these are examples of ISAs that use condition codes as well. Using this, we are going to implement conditional branches. In the conditional branch BR in LC3, observe that we have 3 bits here that will indicate what of the 3 condition codes is going to be taken into account when resolving this branch. So as you can see here, these are the semantics of this BR instruction. And actually this BRC that you see here is just one possibility of the several possibilities that we have for this branch, conditional branch in LC3. The semantics of the conditional branch in LC3 are something like this. We need to check N, Z, and P, which are the condition codes, and we also need to check these small NCP that are part of the instruction. So if our instruction says that this small n is 1, what we will check this big N, or if this P here is 1, we will check the P, the big P condition code. So the good thing is that, well, if the condition, I mean, if this if is positively resolved, then we will store the result of this PC relative addressing into the PC. Otherwise, the value of the PC is not modified, and the value of the PC is the incremented PC. And as you can see here, there are many variations. We have N, if we only check this bit here and the N condition code, or we could combine them, like for example, ZP. We would check this N here, this P here, and these 2 condition codes, big N, big Z, and big P, etc. So let's take a break now. We continue with the conditional branches after the break. And well, let me know if you have any questions. Okay, let's continue. We were talking about conditional branches in LC3, and we were talking about the condition codes. You're going to see more in detail how these condition codes are used here in this slide. This is, for example, this is BRC, so this is branch if 0. What does this mean? This means that we will branch if the corresponding condition code is set to 1. These are the condition registers here, N, Z, and P. Observe that this is 0, this is 1, and this is 0. And our branch instruction contains these 3 bits, small n, Z, and P, where the Z is equal to 1. So what we are doing with these 3 AND gates and this OR gate here is comparing these bits in the instruction with the condition register. So as you can see, the result of this operation is 1. So the branch could be taken. Again, when are these 3 condition registers written? They are written in the last, at the end of the execution of the last instruction that modified 1 register. So if, let's say, before this BRC, we had here some assembly instruction that initialized 1 particular general purpose register to 0, the conditions register is like n equals 0, z equal 1, and p equals 0. Okay? So now one question. What if the 3 n, z, and p in the instruction are equal to 1? That this is the BRNZP. This means that in this logic, the result, the output will always be 1. So this is an unconditional branch. It's a branch that is always taken. And what if the 3 of them are 0? There's no branch, right? No, the branch will never be taken. We will simply go to the next instruction. And actually, we are going to waste some cycles because we could be reading and executing some instruction that in the end does nothing because it doesn't even evaluate any condition codes. But although you might think that this is useless, this is useful in some particular machines. And probably we will talk about this when we study pipelining. Okay, let's now take a quick look at the conditional branches in MIPS. In MIPS, we don't have condition codes. We have slightly different conditional branches. We have this BEQ, that is branch if equal. This is the syntax of BEQ. We have 2 registers that are going to be compared, 2 source registers, RS and RT, are going to be compared, and with this offset, we are going to use this offset to do some kind of PC relative addressing. So we calculate the target address, the address where the branch target address, we calculated using the incremented PC plus sign extend the offset, and also recall that this times 4 is because MIPS is byte addressable memory, and we simply shift 2 positions to the left. Yeah, so the interesting thing here is that with this BEQ, we are not evaluating any condition codes. What we do here is directly comparing 2 registers, RS and RT, and we take the branch or not, depending on the value of these registers. There are variations. We also have branch not equal, so we will branch when the 2 registers are different, or less or equal than 0 for a value of a register that is negative or equal to 0, or greater than 0. So these are variations, but the semantics are very similar, and the way they are executed on the data path is very, very similar as well. Let's now think, because, okay, in MIPS, like having this branch if equal for sure will be useful, right? And we don't have something that is exactly like that. We don't have something like a branch if equal in LC3. So what should we do? We have to compare 2 registers, but we have to do it in a different way. Unfortunately, in this case, again, we need more instructions. And what we are going to do is subtracting the 2 registers that we compared. The 2 registers are, recall, see that here are S0 and S1. Here in this assembly are R1 and R0. So the first thing that we do here is calculating the 2's complement of R1 that will be stored in R3. That's why this addition operation is adding R3 and R0, that is the same as subtracting R0 and R1. We store the result in R4, and if the result is equal to 0, if this R4 is equal to 0, this means that the 2 registers are equal. And if the result is equal to 0, the condition bit Z will be 1. So then this branch here will be taken. We will take a look at an example of this very, very soon. But as I said, there's a trade-off here, same functionality with more instructions in LC3, but obviously the control logic will require more complexity in MIPS. Let's actually take a look at this example on conditional branches for looping. We want to write a program that adds 12 integers. These 12 integers are stored in memory, and they are stored in these addresses, starting in this address 3100. So this is the flow chart of the algorithm. For sure you understand this very, very quickly, right? Because what we do here in this first step is initializing. We load the initial address where the first one of the registers is stored in R1. We are going to use this for addressing. In R0, we initialize R0 equal to 0 because this is where we're going to start store the final results. This is like the accumulator. And in R2, what we are storing is number 12 because we want to add 12 integers, and we are going to use this 12 as a counter. We will decrement this counter after adding each of the 12 numbers. So here we have a test condition. We check if we reach to the end. So we check if R2 is already equal to 0. If it's 0, then we are done. If it's not, we go to this, construct that we have here, where we first load an integer into R4. This is one of the integers that we are reading and accumulating. We accumulating R3, so this is R3 equal R3 plus R4, and then we increment the address R1 because we want to go to the next integer, and we decrement the counter, right? So right after that, we jump here and we again check if this was the last of the 12 integers or not. So let's take a look at the code again. We have here a bunch of instructions. These are the operation codes. We have load effective address and add. Here we have one branch. With this branch, we are going to implement this test condition where we check if we reach to the end of the 12 integers. Here we have a few more instructions. For example, with this LDR, we are going to read the integer from memory, the integer that we will accumulate with one of these additions here. And finally, we have another branch. This branch is going to be used to implement the jump, the loop, to the beginning of this sequence. So here you see the immediate values. And observe that this first branch has the bit Z equal to 1, the other two are 0, so this is BRZ. And this branch here has the 3 bits set, so this is BRNZB. It's an unconditional branch. So let's go through all the instructions. In the very first one, what we are doing is loading in R1 the address. So recall that this R1 is going to contain the address that we are going to access, where we are going to read one of the 12 integers in each of the iterations. This is the accumulator R3. This is R2. We initialize R2 to 12 because we will add 12 integers. And this is branch C. So the very first thing that we do here is checking if the condition code resulting of the execution of the previous instruction is 0. Is it 0? No, it's not. Observe that the previous instruction is R2 equal R2 plus 12. So the result is a positive value. So the condition code Z cannot be 1, it's 0. So this branch is not taken. But at some point it will be taken, right? When will it be taken? When we reach the end. When the content of R2, which is the counter that we are decrementing every time we add a number, is 0. But in case so that's what we are doing here. In case it's taken, we will jump to this effective address that is 300A, that will be somewhere like here at the end of the program. So if the branch is not taken, what we do is we go to memory with R1 that contains the address where the integers are stored, and we load this, we load the integer value into R4 This is just for you to see that these two instructions are both add, but one of them is, has this steering bit equal to 0, the other one has it equal to 1. This is something I already mentioned in the first part of the lecture. So with the first of these adds, we accumulate R4 into R3, and then we increment R1 in order to point to the next integer that we will add. And next, we decrement R2 because we have just added one register, one integer to the accumulator, so we have one integer less to add. And finally, the unconditional branch, so that will always be taken. So what we are defining here is kind of loop. We check if we reach the end of the 12 integers. If we didn't, we read a new integer, we add to the accumulator, and finally, we jump again to the beginning. Okay, so now let's take a very quick look at the LC3 data path. You can compare this to the one you have in the beginning of the slides. This is essentially for you to see some new components that we have added, and these components are useful for the execution of the instructions that we have been discussing. Here we have the global bus, we have this MIR multiplexer that will choose which address is going to be stored in the MIR here to access memory. We have this adder that we use to compute, for example, effective addresses when we have one immediate operand here in the instruction register. We have the sign extension units, that these two are for the address, this one is for the operand, and here we have the condition codes. Recall that these are the 3 single bit registers that are updated every time we write something into a register in the register file. Okay, so now let's start with the second part, assembly programming. So the very first thing that we have to talk a little bit about, you are probably already familiar with this because you have studied programming, but here we are going to focus on assembly, right? So programming, as you know, requires dividing a task into smaller units of works, and each of these units of work is going to be represented by a programming construct. There are 3 main programming constructs. Sequential, conditional, and iterative. Let's take a look at them. What's a sequential construct? Well, it's something is sequential when we have a sequence of operations that are executed one after the other, right? So if we have one task, like this one that we have here, it will be sequential if we can decompose it into 2 subtasks that are executed one after the other. So well, you can see these 2. First part, we run first part to completion, and then we run the second part to completion. Conditional construct, we also have 2 subtasks or 2, let's say, subunits of work, but only one of them is going to be executed depending on a condition. That's what we do with the conditional statements, right? What we can do with the conditional branches, as we have seen, and we will see now again. So we have a test condition. If it's true, we go to subtask 1. If it's false, we go to subtask 2. One of the subtasks could be do nothing. Actually, that it's not required that we have if and else. It's possible to have only if. And once the correct subtask is completed, the program moves onward. And with this conditional construct, we can build if and else or switch case statements, for example. And finally, the iterative construct. We have a subtask that is executed a certain number of times, as long as some condition is fulfilled. So it's something like this. We test the condition here, we run the subtask, afterwards we go again to test the condition. When the condition is no longer true, then we finish the loop. And we can use this for loops, while loops, do-while loops. Okay, so next what we are going to do is take another example where we use these constructs. You will see this in this example, we are going to use the 3 types of constructs. And this program is about counting occurrences of a character. So we are going to input one character from the keyboard, and we are going to search in a file, in a text file, for this character. And we are going to count the number of occurrences. So the input is taken from the keyboard using the trap instruction. I will briefly talk about the trap instruction next. You can read more about it in the book, Patan Patel. And the file finishes when we reach the EOT, the end of text. This is what is called a sentinel. So when we reach the EOT, when we reach the sentinel, we know that we need to finish, we have to finish the iterations that will allow us to go through the entire file. In this case, in this particular example, EOT is equal 4, and then we will output the result, the total number of occurrences to the monitor. This is our algorithm. I will explain it in a minute. But here you can also see that here on the bottom left part, we have the different programming constructs so that you can recognize them in the algorithm. So first we have some sequential constructs. What we do here is initializing R2, that is going to be the counter of occurrences. In R3, we have the initial address. This is a trap instruction that we use to take the input from the keyboard. And now we go to the file, we go to memory, and we read one char from the file. Here, we check if the chart that we just read from memory is the end of the file or not. If it's the end of the file, we will finish. If it's not, we will execute this subtask here. And observe that this subtask is composed by some conditional construct, where we check if the value that the chart that we just read from memory is the same that was the input from the keyboard or not. In case it is, we increment the counter, and then we increment the address to go to the next char in the file, and we read it. We read this char from the file. So when we are done, we prepare the output to output it to the monitor. We output the counter and we stop. Okay. Yeah. Well, this is just one slide to talk briefly about the trap instruction. This is useful to invoke operating system service call. We can, in our program, we can ask the operating system to do something for us. This is what is called a service call. For example, input a char from the keyboard or output to the monitor or halt the program. We are going to use these 3 actually in the program. This is the program. We are not going to go through all the detail of this because actually we have already explained this in the previous slide. But here we initialize the counter, we load the initial address in R3, the initial address where the file is stored. Then we input, we take the char from the keyboard. Here we read the very first char in the file. And here, what we are doing with these 2 instructions here, observe that we are subtracting something that is in R1. We are subtracting 4 from something that is in R1. So this is R1, the char that we just took from the file, minus 4. If the result is 0, this means that they are equal. And if they are equal, this means that this char was the end of text. So if it's the end of text, we will go to the end of the program. We will jump to this address here, and we will execute these last instructions that allow us to output the counter to the monitor. But if it's not, if this char is a regular one, it's not the end of file, what we are going to do next is subtracting the char from the file that is containing R1. Recall that we loaded it here into R1, and here what we are doing is calculating the 2's complement, and here what we do is adding this 2's complement to R0, and R0 contains, what contains? Contains the input char that was taken from the keyboard. So if the result of this subtraction is equal 0, what will happen? We're trying to count the occurrences of one particular char that is in R0 in an entire file. Let's say that this chart is A. We search for A in the entire file. So every time we find A in the entire file, we count 1, right? So if the input A is equal to the char that we took from the file that is containing R1, we have to count it. So if it's not, we will jump to the next instruction where we increment the address. But if they are equal, we have to increment this counter. Okay, in both cases, we need to read the next char from file, and finally, this unconditional branch that brings us to the beginning of this code, where we again go to memory, read one new char, compare it to the char that was taken from the input, and in case they are equal, we increment the counter. Well, you can take a look and read the code more carefully. The most important thing here, anyway, is that you understand that with these instructions, like the conditional and unconditional branches, we can build programming constructs, like, for example, this do while. Observe that with these two instructions, we are checking this end condition here. We are checking this condition. If we check if R1 is equal to the end of the text or not. And with this unconditional branch here, what we do is jumping in order to do as many iterations as necessary for this do-while loop. And something similar is what we are doing here when we subtract the char from file from the input char for the comparison, and in case they are different, we jump. In case they are equal, we increment the counter. And this is an if statement where we are comparing the contents of two registers, R0 and R1. Okay, we will continue talking about programming. We will go next to assembly programming in MIPS. It's a little bit higher level, so probably easier to understand. But now let's briefly talk about debugging, because you have seen that it's quite complex, right? This matching code. So it shouldn't be difficult that we make some mistake. And in case we make a mistake, we need to fix the problem. We need to find the error. So that's what we call debugging. Debugging essentially means finding where the program has errors. Usually what we want to do is like dividing the program into different parts, modules that are going to study, analyze in detail, independently. And in the interactive debugging, what we will do is put some values in memory and registers that we are going to use to test the code, execute some instruction sequences, and current debuggers allow us to run several commands like run, that simply runs the program until the end or until it reaches some breakpoint or a step that allows us to run step by step. You're probably familiar with this if you have used some debugger when programming with some high-level language code. It is possible also to stop the execution when we desire, using some set breakpoint command, and it will always be necessary to check what's the value of memory and registers when we are running this debugger. So let's take a look at multiplying in LC3. I mean, I'm not going to go into the details. Essentially, we need some multiply code in LC3 because recall that we don't have multiply operation in LC3. So the way we can implement multiply is by adding a certain number of times a number, right? So that's what we more or less do in this code. Essentially, we have two input registers that we want to multiply. These are R4 equal 10, R5 equal 3. You know that the result should be 30, but for some reason, this code produces a result that is 40. And what went wrong? So, well, what we have to do is checking our code. Obviously, this kind of annotations can be useful to understand the code. And we have to go instruction by instruction, checking what are the values of the registers and see if what went wrong, right? So what we are doing here is accumulating the output into L2, the result of the multiplication, and see that in each of these iterations, what we do is adding the contents of R4 to R2, and we do this a certain number of times. And this number of times is defined by the initial content of R5. So what we do is adding R4, R5 times. So that's essentially a multiplication. But for some reason, this program has something wrong. It produces some wrong results. So what we can do is going step by step to execution of all these instructions. You see what is the program counter for all these instructions, what are the values of the registers involved in each of these steps after the execution of each of these instructions, and observe that we could have reached the correct result right here, but instead we continue the execution. The branch should not be taken at this point, but it was taken, so we had one more iteration, and this means that the final result, instead of being 30, is 40. So what was the problem? The problem was that instead of jumping, branching, when the condition code is, when 0 or positive, when the condition codes Z or P are equal to 1, we just need to branch when the condition code P is equal to 1. So we should branch only when register 5 has positive value, not when it has value 0. This is debugging. I mean, I think that you are already familiar with this. This can more easily be done if we use breakpoints. We don't need to go step by step executing the instruction and checking the contents of the register. In this particular example, we could have just had a breakpoint in the branch instruction, and at the end of each iteration, check what are the contents of the registers. And still, the program, even though we might have fixed it with this correct instruction, it still has some problems for some values. So think about the case where R5 is equal 0. So I leave this for you to think about it. Okay, so now we are done with LC3 assembly. Let's briefly talk about conditional statements and loops in MIPS assembly. So how can we implement an if statement in MIPS? Something like this. If I is equal j, we execute this, otherwise, or else we don't execute anything, right? So the way we do this in MIPS assembly is using branch not equal. Observe that branch not equal compares two registers, R3 and R4, and jumps in case these two registers are not equal. So if they are equal, you will execute the next instruction. If they are not equal, you will jump to somewhere, some other address, some other instruction labeled by this L1 here. So if S3 and S4 are different, we go to this sub instruction that corresponds to this high-level code instruction that we have here. We can also implement if-else, and in order to implement the if-else, we need to use unconditional branch and like J, and also conditional branch like branch not equal. So here we want to execute F equal J plus H if they are equal, else we subtract I from F. So we check if S3 and S4, S3 contains I, S4 contains J, are different. If they are different, we go here to L1 where we subtract. If they are equal, we execute this addition corresponding to this addition in the high-level code, and then afterwards we jump to done in order to skip the subtract instruction. Observe how we can change the execution order by using this conditional branch and unconditional branch. For the while loop, what should we do for while loop? Well, we also need something similar. We also have to use BEQ in this case to check the condition. In this case, the condition is here. We compare this POW to 128. Here in this assembly code, in S0 we have POW. In T0 we have 128. If they are equal, we jump to done because it's the end of the while loop. If they are different, we go through the body of the loop. And when we reach the end of the loop, we unconditionally branch to the beginning of the loop. We check again the condition. When the condition is not true, we go to the end of the while loop. And something very similar for the for loop. And actually, if you compare both codes, you will see that they are implemented exactly in the same way in these two particular examples. It is slightly different when we have to check in the for loop a less than comparison, and this one that we have here. In this case, we need to use this set less than instruction. The semantics of this set less than instruction are here. You are familiar, I think, with these semantics, right? We compare these two. If S0 is less than T0, we set T1, otherwise we clear. We set it to 0. So what we are doing here, we are comparing these two registers that contain respectively I and 101. We compare them. If they are equal, we jump, because this means that we are in the end of this for loop. If they are different, that means that I is still less than 101, and we keep executing the body of the loop. This SLL is simply a shift left that when we shift one position to the left, as you know, is the same as multiplying by 2. Okay, now let's take a look. We have already taken a look at if-else statements in MIPS, also in LC3, and how to implement loops in MIPS and in LC3. Now let's finish taking a look at how to work with arrays in MIPS. I already mentioned this in the beginning of the lecture. Recall that we need to somehow store the address of the array, the beginning address of the array, in one register, because the way we access memory, and specifically in MIPS, it's always this way. We need to have the address in one register in order to compute the effective address, right? So as we saw before, and here you have the code again, if we want to access this array, well, the very first thing we will do is store in the beginning address, the starting address of the array, that is this 1234800, into some register, and afterwards we can start using that address for reads and writes. The way we do this is using load upper immediate and load and or immediate. Recall that this 1, 2, 3, 4 will be stored in the 16 most significant bits of the register S0. And here you see some example code. We want to update the values of these arrays, the elements of this array, array 0 equal array 0 times 2. This is something that we are doing here. We read with load word array 0. We multiply by 2 by shifting one position to the left, and then we store the result in the same address, S0 plus 0, S0 plus 0, as you see. But the very first thing that we had to do is storing the initial address of the array into register S0. Okay. Well, we continue with MIPS assembly and programming. Function calls. Why do we need functions or procedures? Why do we need them? We use them when we want to reutilize code, right? Like some kind of frequently accessed code. And this is good because that makes the program more modular and readable, and also it's going to be easier for debugging, as we mentioned before. Functions, as you know, receive some parameters, some arguments that are passed by the caller function and return some value. That's something that you're already familiar in high level language code. This is, for example, one main function, and this main function, we call this subroutine or procedure or function sum that computes something. In this case, it adds two values A plus B. So we say that main is the caller, sum is the callee. There are some conventions here that you need to know. I guess that you are already familiar with most of them. The caller passes arguments, jumps to the callee. That essentially means changing the value of the program counter to point to the address where the function starts. The callee performs the procedure and returns a result to the caller. And it also returns to the point of call. Actually, the return address is the next instruction to the instruction that called to the function. That is called the return address. These are also things that you have to know to use function calls in MIPS and in LC3. In MIPS, we call using this jump and link that we presented yesterday. In LC3, there are two possibilities. One is JES-R, the other one is JES-RR. They have the same functionality, but the only difference is the way they compute the effective address. The only difference is this is PC relative and this is register-based addressing mode. And in order to return from the procedure, we also have a specific function. It is a jump register in MIPS. It is RET, read from return from subroutine in LC3. In MIPS, there are also conventions for the input arguments, the argument values, these registers A0 to A3, and for the return value. And here you can see a very simple example. We jump and link to simple. Here in simple starts one function. This function is very, very simple because it's just like jumping and right after that returning to the address that is stored in this return address register. This return address register contains, and actually this is stored in this register, address register, so the return address register by the jump and link instruction. It stores there the return address. So similar thing is done in JES-RR, where the return address is stored. Instead of, we don't have this RA, we have R7, but essentially the same thing is done. You have here a more complex example. You can take a look at it by yourself. This is, well, you see that we have some input argument values storing a register. We have the return value. Observe that we jump and link here to this function, and we will return using the return address register. And well, you can take a look at the code more in detail. The only thing that I want to mention is that observe that in MIPS, the number of registers is limited, even more limited in LC3, right? So for this reason, it's useful to have somewhere, some part of the memory where we can store the operands that are being used by the caller function in order to avoid that the registers that contain these operands are overwritten by the callee function. So that's the reason why we need the stack. And as I said, this is like a stack, like a LIFO queue where you start putting elements there, and at some point pushing elements there, and at some point you pop them because you want to use them again. So you can see for this, let's say that here in this specific function that we presented in the previous slides, we have some registers like T0, T1, S0 that are useful for this function, but maybe they were also in use by the caller function. So the very first thing that we have to do in the beginning of this function, of this subroutine, is storing the values that we have in S0, T0, and T1 into the stack. In order to do that, we need to reserve the stack starts in the address that is stored in this SP, that is called the stack pointer. So what we do is reserving some space in the stack by subtracting, in this case, 12 from the stack pointer. So we move the stack pointer and we reserve, in this case, 3 memory positions in order to store there S0, T0, and T1. Then we execute the function, and at the end, we can read the values that we saved and put them again in T0, T1, and S0. Yeah, so this is the way we use the stack to save registers that can potentially be overwritten by functions that are called from a main caller or a main function. Because this takes cycles, there are some conventions. It's not necessary to save in the stack all the registers. We will just save those registers that are called preserved registers, and those in MIPS are registers S0 to S7. Now you can understand why they are called S0 to S7, because they are saved registers. They are preserved. Temporary registers are not preserved. So now we reach at the end of the lecture. These are all the different things we have presented today. We finished with the ISA in MIPS and LC3, and we talk about assembly programming also in LC3 and in MIPS. If you have any questions, please let me know. We can talk later also. Otherwise, I hope you have a nice weekend. Thank you very much for your attention.